Welcome to another video explaining the universe using the particle model. Before starting the presentation, I want to remind you that Dave and I are writing a book, and this is a short video showing the logo of that book. Yes, the name of the book is Principia Mathematica 2, and you can find out information about it at that site. Well, today's video is about the electromotive force, otherwise known as EMF. By the way, you can translate electromotive force in reverse by saying it's a force that moves electrons. That's exactly what it means. I'm going to talk about that and the railgun, which includes back EMF. Okay, so here are the types of EMFs. This is from Wikipedia. In electromagnetism and electronics, electromotive force, or EMF, is denoted by epsilon is measured in volts. It is the electrical action produced by a non-electrical source. Devices known as transducers provide an EMF by converting forms of energy into electrical energy, such as batteries, which convert chemical energy to electrical energy, or generators, which convert mechanical energy to electrical energy. At least that's how they say it. Now, the counter-electromagnetic force, or CEMF, is also known as back EMF, is the electromotive force or voltage that opposes the change in current which induced it. Counter EMF is the EMF caused by magnetic induction, and that all involves Faraday's law, electromagnetic induction, and Lenz's law. That's the standard explanation. Well, when I did a video on the battery a couple of years ago, I got to a point where I was trying to explain how this worked, and I couldn't get the electrons to get a force that caused this electrons to go that way. And that's the EMF force I was looking for, because I saw a balance. Well, recently I went back and looked at that and re-looked at this electrochemical series, which is quite interesting. It takes these half reactions. By the way, the wet cell battery, there's a half reaction here, and there's a half reaction here, and you add the two together the way they did in this graphic, 0.3 and 0.76, and you get a 1.1 volt voltage across the battery. And apparently they've done some measurements, and frankly, I don't know how they do this, because their reference point here is hydrogen, which has a 0 value, and you have some half cells that give a positive voltage and some that give a negative voltage. And let me just say at the start here, a voltage is normally a voltage gain, not a voltage loss, especially with a source. How do you have a source with a negative gain? So having a negative number here just doesn't seem right. And the chemical process here is quite strange. In a sense, it starts over here with the zinc, where the zinc interacts with the electrolyte and emits 2 electrons. And the 2 electrons come over here, and they combine with copper ion and make copper back again. Well, prior to that, copper interacted with the electrolyte to make sulfate and a copper ion. The electron these two only go this way. That's it. It's done. the rest of the theory says that the exchange of ions is what continues the circuit. So even though we often think of electrons flowing all the way around, they're saying no, they go from here to here, stop, and then the ions transfer here. And that's how they say it works. Yeah, the negative isn't good. So this is strange, and so I have a problem with their explanation. So I decided to redo this and get rid of this negative stuff. And I took this chart and I used hydrogen as a baseline down here because it's 0. I made them all positive and gave it a value. This is the voltage from 0 to 3.05. But for the particle model, I often assign a voltage to each G1. In this case, for convenience to make whole numbers, I'm assigning it 0.01 volts per G1. So you divide that into 305, you get 305. So a lithium, a half cell, is going to give off 305 G1s. Well, in this case, you can see that the copper is going to give off 34 G1s. The zinc is going to give 76 G1s. If they both half sides both give off 134, 176, you get the 110 G1s that are flowing around, and that gives you your 1.1 volt. Well, here's the interesting thing that I really figured out here. I'm not sure you're aware of it, but when a voltmeter reads voltage, when they do this measurement, there's a time base. Let's assume for a moment it's 1/10 of a second or 100 milliseconds. So you put your meter on the copper half cell, and every 100 milliseconds it averages the value, and then you get 3.34 volts. And then another 100 milliseconds it does it again. Well, when you do the zinc is down here, and you do that same thing in 100 milliseconds, you get 76 volts, 0.76 volts. You apply that to here, it says that you're getting you're getting more here than here in the same time interval. So I claim that this voltage measurement is actually measures the chemical activity. This is the thing I didn't say before. There's an activity, there's a release of 34, there's a release of 76 in each half cell, and there you have it. Well, I already mentioned I did one on a battery. It was back in June of 2018 called Battery, the Wet Cell. By the way, there's been some people who've actually viewed this recently. And it was in that I couldn't get the electrons to go around this way. Well, now you saw the equations the way they were, how it emits 2 and it stops here and recombines with copper, saying, no, that's not the way it is. And that's not what that electrochemical series says. It says it's giving off 34 G1s here and 76 G1s here to give you 110 total around the loop. I maintain they're both giving off electrons. Copper and zinc both emit G1s, and the amount can be determined by the voltage rating. How many there are in the same interval of time. Zinc releases 76, while copper releases 34. Zinc, that is 2.23 times more active than copper. They only give off 2 each, assuming that chemical type of reaction is right. They only give off 2, yet there's, in that same interval, this has 2.23 times, which tells me this has 2.23 interactions more than this. Or, you make it a whole number. For every 100 copper, there's 223 in the same time interval. This is more active than this. That's what the voltage is telling me. Okay, but what it tells me further is that there are more G1s here in that interval of time than there is here. And now I have an imbalance of mass. I have more mass here, less mass here, and you'll end up with a net force pushing the electron out the negative terminal, which is what I was trying to do in my June 2018 video. So that finally works. By the way, most chemical equations don't show the electrolyte. They also don't know that you have to add heat. If you remember my explanation, the chemical interaction is a matter of the atoms vibrating. Copper atoms vibrate, the electrolyte vibrates, they hit together, they break loose electrons. It's a mechanical process, even though it's called chemical when we write chemical equation, but it takes heat. If you don't have heat, if you get zero down colder and colder and colder, you have very little motion, no G1s released, no battery. Yeah, and you could probably extend the life of a battery if you stored it in the refrigerator. I've heard that in the past anyway. So that's the answer. That's why the electrons go around, and the electrochemical series actually is a measure of the chemical activity here versus here. Okay, let's move on to the generator. And from Wikipedia, generators convert mechanical energy to electrical energy. Actually, it starts with gravity, if I might say so. Gravity is pushing down on the water. Water comes through the canal, turns the turbine turns the generator generates electrical power. This is a transformer and distributes it. They're saying mechanical because of the turbines turning in a mechanical sense, but it's really gravity that's causing. Of course, humans build the dam such that there is this flow of water. Okay, so how does that generator really work? And I'm going to start with the DC EMF, believe it or not, because even though there is a water flowing, it turns the turbine, you get that, there's something else going on. There's an electromagnet here that has a battery that puts DC current through the coil of the electromagnet, creating a north-south electric field. This drawing is based on current. This is based on current, not electron flow. But nonetheless, it starts with the battery. And when you first turn on a generator, they're relying on having a voltage source. So even if it's a power supply that's powered with AC, if there's no AC to do the power supply, you got to have a DC source to kickstart it and get the magnetic field flowing. So the first thing you have is a magnetic field flowing. Then you turn this. This is turning clockwise. And as this coil and the rotor, this turning part is the rotor turned by the turbine. And as the wire cuts through the magnetic field, they say there's an induced current. And actually, in this one, it actually shows the north is on the left, south is on the right. The conventional magnetic field is that way. When it's vertical, it has zero EMF. When it's horizontal, it has a maximum in one direction or a maximum in the other. Then back to vertical gives you zero. So as it turns, you get this, and it increases the amount of induction increases and then decreases in a sinusoidal way. Yes, and if you want a 60 cycle with this simple model, if you want a 60 cycle, the turbine over here has to turn at 60 cycles per second to generate a voltage of 60 cycles that we get in our home. Well, what they just say there's an EMF over here. That's a DC EMF that I just explained about the battery. That's the G2 gravity that was pushing the electrons around the circuit, the wet cell battery. Over here, the EMF is associated with the load. Yeah, and it's an AC EMF because the way they describe it, it's AC. Well, that to me isn't where that belongs. If we're going to talk about the AC source, this is the load, not the source. Yeah, you can say that there must be an EMF here or there wouldn't be current flow, but it's the load. Over here is this is the source, and the somehow the magnetic field induces a current in the wire, and so the source is in the coil. So the ACMF source is here. This is the load, and that's the curve. So that's their explanation. Uh, this is this is talking a little bit more about induction. Induction is kind of difficult in a way, um, and I wanted to make a basic point here that G2 gravity causes G1s to turn corners. I've done many circuits, and I just picked this one off the internet a while back from some video. And here's the G2 particle field generating forces, and I was explaining how G1 particles coming out of the battery get accelerated here and then slow down, and how you have G2 forces this way, a strong force here and a strong force up here. So as it comes to this point, you have two forces, one slowing it down, one causing it to turn. And yes, you can have it turn a corner here, you have it turn there, and come back here, it turns a corner. It does it all the time, and we think nothing about it. And I'm saying G2 gravity is the force that moves the G1 around. Second point, I've often talked about FM radio transmitters and radios. And in this case, very simply, the G1 hits the antenna, scatters in all directions, goes over here, enters, turns the corner, and goes down into here. Uh, Again, we think, okay, well, the FM radio signal transmits, the antenna receiver receives it, but in this case, I'm specifically talking about the flow of G1s. And it can enter a wire. Here's a flow of G1s, it enters the antenna, it turns right. That, I'm saying, is the same thing as the induction that I was talking about in the previous slide. And so here's a different picture, magnetic field, but in the case of the particle model, this magnetic field is actually a G1 flow. And just like the antenna, it hits this and turns. Why does it turn? Because it has a G2 force field here that turns it. Once it starts turning this way, it'll flow here. On this side, it's the other way around because of the way it cuts. Now that part I'm not explaining, but this ends up being exactly identical actions. If you look at this from the top down, it's making a right turn. If you look at the same motion upside down, it's also making a right turn. So the magnetic induction is a matter of G1s happen to pass through the wire and the G2 force field forcing it into to flow in the wire. The current actually comes from there. The AC EMF is here, out here where this goes to, where they had resistor as a load, has an AC voltage across it because it got these slip rings to make it work. Okay, so much for the battery and for the generator and induction. A railgun. I stumbled across a simple example. I was looking for back EMF, and a railgun happens to be an example of that has a back EMF and a simple model to explain it. This is from How Stuff Works, and let's read this. It's a kind of interesting background. Gunpowder has long been the propellant of choice to launch a projectile from a weapon, but the fine gray powder does have three major limitations. Gunpowder must be carried with the projectile, making the entire round heavier. To say nothing of the fact that it's a danger to our own soldiers, because if enemy fire hits these projectiles, our own ordnance is going to kill us. Ordnance based on black powder is volatile and so difficult to handle and transport. It's even life-threatening. Here's an interesting point. The muzzle velocity of projectiles propelled by gunpowder powder is generally limited to about 4,000 feet, or 1,200 meters per second, feet per second, meters per second. Is it possible to overcome these challenges? One solution is the electromagnetic railgun, or railgun for short. Using a magnetic field powered by electricity, a railgun can accelerate a projectile up to 52,500 feet per second, or 16,000 meters. Here is 4,000, here is 60, that's 4,000 times. No, excuse me. It's almost 16,000 because this is meters, this is meters. It's 1,200 to 16,000, which is almost 16 to 1. And while current Navy guns have a maximum range of 12 miles, rail guns can hit a target 250 miles away in 6 minutes. Interesting. Well, here's two pictures of a rail gun. Yeah, look at that. That's a military rail gun with this. The rails are inside here. This is a projectile being rolled around. This is a projectile up here, probably being set in, and they elevate the thing to get a certain elevation, certain direction, and they want a certain velocity, and that's the key point. They need a certain velocity to hit their target. There's a rail gun. Colt 1911 railgun. Some guns I read somewhere that they're called rail guns, but often they're coil guns. It's a little bit different mechanism and really don't have rails, ironically. That's just two examples of rail guns that you may have, if you're familiar with firearms at hand, you may have known that. Well, here was a video I found on back EMF, and a nice simple, here's a DC supply. Here's one rail that's positive, and there's another rail that's tied to the negative, and we've got a rolling bar here, and a current flow. This is all current flow here, and a magnetic field, vertical magnetic field in this case. And this is going to demonstrate a back EMF. It involves the traditional answer is, this is the reason you have a back EMF is because of Fleming's, let me put my left hand rule, because of Fleming's left-hand rule. That's the whole explanation. No, what the rule tells you is just direction of things and what the resultant motion is. But it doesn't tell you what makes it move. It doesn't say anything about what makes it move. Sometimes in words it does, but the left-hand rule pushes right, is what they show, and the right-hand rule pushes it back. That's the back EMF. The rod keeps accelerating until the two forces, because they got actually, I'm going to show this this way. It's kind of hard. Magnetic field going down, current this way, forces this way. If you can see it, and so when the force builds up, the back EMF and this EMF builds up, what happens is the back EMF actually slows it down, and when it's equal force, you have constant velocity. If you design the rail gun right, the certain length of rail, certain voltage, certain magnetic fields, and you can do all the engineering, proper engineering, you can get it to the point where you know based on the voltage here, once the angle is set, the direction is set, and you know what all the characteristics of the gun, all you need to do is adjust this to get the right velocity and trajectory to hit the spot you want to hit. If you don't control it, if you don't control the speed, you don't know exactly where you're going to hit. It gets a little bit iffy. If you take away this magnetic field, theoretically, it says in this video, theoretically this rod will roll forever and keep accelerating faster and faster, assuming you had a very long rail, a very long rail. But the magnetic field is what adds it. When you add that, it gives us this back EMF. Okay, I don't know. Had a point when I put this slide in, and I lost it, so we'll move on. Well, here you go. Left-hand rule accelerates, right-hand rule decelerates. No physical explanation. But this gets closer, even though they're using a physical explanation. They do show here that as the current flows from here, turns a corner, by the way, right? It turns a corner again, goes back. This is the projectile here. And they got a magnetic field that sets up here. And they're saying, yeah, it's the Fleming's left-hand rule that causes this to move. Well, that's the standard explanation for the force in that direction. Not sure what what they say is that the left-hand rule induces a reverse current. That's what the text said earlier when I read about it. It induces a reverse current, and that slows it down. That's what they said. This is what I say is happening. Battery, G1's flowing out here, turning the corner here, turning the corner here. The magnetic field is a spiral. You can see this spiral here. I've drawn it, and it's moving this direction. And so there's by the way, one of the serious parts of this railgun for in some, you get up to 1 million amps of current to generate enough magnetic field to push these huge projectiles, that you want, and it's a huge mass they're pushing. So they got to have a lot of force, and the more current they have, the stronger the magnetic field. And you got this on this side, you got the magnetic field clearly. Could clearly, the G1s could clearly be pushing on this rod. It's a little harder to understand whether how this really happens is that as the G1s, as the magnetic field, turns around and goes this way, it's pushing against the rail, and you get a recoil action pushing the other way, action and reaction, so to speak. Harder to visualize, but possible. The other one is that the G1s themselves hit and push. That's what G1s can do. The G1s can hit and push the earth in terms of gravity. They can certainly hit and push a rod that's a round rod that rolls. Anyway, then so you get the same recoil action when the G1s hit this rod and kick the rod. Since it's coming from the rod, it has a kickback on the rod and pushes it this way. Two answers, maybe both are right. Maybe the number of G1s pushing directly as they go through the rod, usually, even though you have a lot of them, the number that are pushing, most of them pass through. Most of them just go right around, and only a few of them hit. So maybe that favors the magnetic field as it. But where does the back EMF come from? That's the question. Well, I told you earlier you had to have this vertical magnetic field. I'm looking at this round rod from the end, and the magnetic field is going down, and on the backside over here, if you look at it, you've got the circular one going down, and it comes up on this side, down on that side. So it goes up on this side, down on that side. This is the same explanation I gave before when they talked about measuring the electron mass. Uh, these two are being added together. You got a field G1s here, you got G1s here, you got twice as many G1s, but with minimal interaction. You're going to lose some. There's going to be some collision. They're going to scatter and go off, but you're going to have minimal collision because they're going the same way. Here, you've got G1s coming down, and you got these coming right up at them, and you got head-to-head on collision. You have more collisions. Therefore, what I'm saying is that there are more G1s clustered here at any instant of time and fewer here, giving a net force pushing this way, and that is the back EMF. Remember, you got G2 particle field all the way around it, and the forces are, if everything is balanced, the forces are all equal in all directions. But when you get an imbalance, you get a force pushing G1s from here to here. By the way, same thing happens in cloud-to-cloud lightning. There's one cloud with a lot of G1s. There's another cloud with a few. When the situation distance is right and the force is right, you push G1s this way and you get lightning. Just a side point. Okay, as a summary, again, it's the activity. The EMF is G2 gravity here. It's the activity that causes, this is more active on the zinc side than the copper. You get 34 G1s here, 76 G1s, 110, and you have a flow that way. The net flow is in this is large mass, this is small G2, you get G2 force pushing them. That's why the electrons flow that way. And it's all because this is a higher active than that one. Generator, the induction, G1s flowing into a wire where there's an F2 force that can push either way. You get them to turn here. By the way, there's a little piece that I don't have here. Do they all move this way, or do some move the other way? The answer generally is yes. It's always a case of which one has more flowing in this direction than in that direction. It isn't all one way. And exactly how to explain why it should end up this way when this looks balanced. I got the same problem here as I had with the battery, but I resolved it with the battery, but I haven't finished that there yet. And of course, this is the back EMF caused by the interaction of two magnetic fields, and giving a back EMF pushing this backwards, such that when the pushing force and the back EMF caused by this is equal, this will then move at a constant velocity. So if you know the length of your rail, you know the amount of voltage, and you know how much force you got here, you can determine what the velocity is going to be leaving, and you can hit your target. My name is Bobby Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.